Hi, my name is Bob Lochner, and I am a physics and math student at Hillsdale College. I'll be a senior this coming year, and this summer I worked with Huashan Li, Zhigang Wu, and Mark Lusk, and I studied functionalization of 110 silicon nanowires. So to begin with, I was modeling wires using a program called DMOL3, which uses DFT to predict ground state properties of silicon nanowires. So the 110 nanowire, we obtained a unit cell, and the atomic positions of these were determined by taking bulk silicon and carving out a wire with set diameter. The diameters I chose were 1.2, 1.6, and 2.2 nanometers. I have a little summary here of density functional theory, the main point being that the ground state properties of a material are all functionals, or can all be described as functionals of the electron density. One of the first things I did was actually reproduce some results from 2004 in which Zhao et al. Showed the size dependence of silicon nanowires, and that effect is that when a nanowire is smaller, the band gap increases. That effect is because of the quantum confinement effect. So when the wire gets on the order of the exciton Bohr radius, which is about 5 nanometers, the electron and hole pair are confined, and your HOMO and LUMO levels separate. You get a larger band gap, and so that's interesting. Another thing I researched this summer was I looked at surface reconstruction, and so the silicon nanowire with the 110 orientation has on one side a plane or surface facet of 001, and that on planar silicon or on the wire originally has dihydride structure, so it has 2 hydrogens or 2 ligands per surface silicon. Then it reconstructs to leave only a single hydrogen or ligand and forms a dimer of silicon, and that's interesting. The resulting structure is about 0.5 eV, lower energy per unit cell, and so that was also a known result for some wires, but we showed it with the 1.2 nanometer and 1.6 nanometer wires also. An interesting thing I checked was to see if the dimers were aligned or antisymmetric, and I found that it was lowest energy if they were paired together or aligned. Finally, another thing I studied was band gap and the effect different ligands have. So I compared my data to Huashan Li's data on silicon quantum dots, where she used the exact same ligands: hydrogen, amine, methyl, sulfur hydroxide, fluorine, and hydroxyl. And so the results we noted were similar trends for wires and dots, and also a highly tunable nature of the HOMO-LUMO levels, because as you can see here, fluorine drops the HOMO-LUMO levels significantly. And while these results are not necessarily good quantitative predictions, they are good qualitative predictions, and so that's something interesting to know. An example of the qualitative usefulness of DFT is the fact that although the band gap of bulk silicon is about 0.7 eV in DFT, the actual value is about 1.1. So although we don't know from DFT the exact values of the band gap, we do know that it increases as diameter decreases. So that is a pretty quick summary of what I've been studying this summer. I intend to move on to look at oxidation and passivation of wires in the sense of a nanowire if put in an oxygen environment, oxygen can get into the nanowire and create silicon dioxide or silica. And if that were to happen, a lot of the properties of the wire change, and the effective diameter of the crystalline silicon becomes much smaller. So in order to keep oxygen out, we're looking at passivation with different ligands, and one way we're doing that is to think that thermally it doesn't make sense to create a model in which oxygen does not get into the wire. So we assume oxygen will get in, and we're looking at binding energies and energy of the structure to determine if we can make it more energetically favorable to stay outside the wire than inside. And so Hua-Shan Lee has been studying that with silicon quantum dots, specifically Si29, H24. But I will hopefully soon be looking at this this fall from my home institution of Hillsdale College.